there's some complication. In repeated you'll have to use the method of undetermined coefficients. So given this, if we have a 0 eigenvalue, repeated eigenvalues, we'll have different things happen. So let me show you what happens here. All right. So here, let's go ahead and do this. So this becomes -2, 1, 0, -2. So we're going to find the eigenvalues. We're going to find the lambdas here. So when we find that, can we actually just read these off? Yeah, we can just read these off, right? We can literally read these off as lambda 1 equals lambda 2 equals -2. Why? Because this is upper triangular. And so the eigenvalues are just the diagonals. And so this is what we call a degenerate system. And this means more to a numeric degenerate system. And so this means something more to numericists than it means to you guys, so people who do numerics. When you have repeated eigenvalues, numerical things just tend not to work as well. Just the way it works. So anyways, let's go ahead and find, so our next step would be to find the eigenvectors. So v lambda. So in this case, I'll have -2 x1 plus y1 equals -2 x1. And then I'll have 0 x1 plus 2, -2 y1 equals -2 y1. This translates into y1 equals 0, 0 equals to 0. So our vector here is 0 in the y component, free in the x component, so we're going to put a 1. Okay, so that's our vector. So here we have a y1, right? We have a y1 equals to e to the -2t, 1, 0. What about y2? Well, we don't have it, right? Either we don't have it or it's the same and it's not linearly independent. So we have a problem. So let's go back. Could I solve this one using a different method? Sure. This is a partially decoupled system, right? AKA that one's partially decoupled. So let's see what happens. Let's see what's happened and solve it and see if we can't get to our other answer. So let's do that. So here, we're going to use this as a partially decoupled system. So this is partially decoupled. Partially decoupled. Okay, so this is partially decoupled. So how do we solve that? Well, we solve this one first. So this one equals y is equal to y naught e to the -2t. Okay. We've solved this one 10,002 times. I assumed if I write out the answer, you know what it is. If you don't, kind of go look it up. Okay. We're going to find out what dx dt is, and then we're going to plug in. So it's going to equal to -2x plus y naught e to the -2t. All right, so we're going to guess. So here we're going to rewrite this a little bit. How much space do I got? Okay, space. So here I'm going to write this as dx. Or actually, I'll just write this as x prime plus 2x equals y naught e to the -2t. Okay. So I'm going to save ourselves some time. If I make the normal guess of e to the -2t, which I would guess for this thing when I take the homogeneous version, right? It fails, right? The normal guess here would fail if I did the homogeneous plus the particular, right? Because we know the homogeneous would be this, so if I find the particular, it ends up falling apart. So here we're going to have to guess for the solution. It takes a little bit of work. We're going to guess, you come to find out that e x of t is equal to t e to the minus 2t, which isn't very shocking, right? This isn't very shocking based off of everything we've learned. And so x of t all put together, right? So this is what we'll have to, hold on. This would be our xp guess, right? Xp guess ends up being this. And then x of t ends up being y naught y naught. Oops, do I have this the wrong way? Oh yes, so y naught t e to the minus 2t, because that's what our guess is. And so it ends up being y naught once we actually crunch through the numbers, plus our homogeneous solution. Our homogeneous solution, of course, was e to the minus 2t. So this is our homogeneous solution. This was our particular solution. Okay. I can put x homogeneous real quick. That makes stuff a little bit more clear. Okay, so here's our homogeneous solution. This was our particular solution. So if you guess this, it fails. So you have to use this as our particular solution, and then you get out. This is what tends to fall out based off whatever your initial x value was. And so here we'll have our initial, and we'll put in our y right below it. So we'll have y naught e to the minus 2t. Then I'm going to write this in vector form. So if I write this in vector form, here I get e to the minus 2t, x naught, y naught, plus t, plus t, e to the minus 2t, y naught, 0. Okay. So here's our solution. How do we get this? We just use partially decoupled system. But I want us to look at something real quick. Here we have one solution. Is this close to this? Yeah, this is definitely an eigenvalue vector for this, right? But it's a very particular eigenvector. In fact, I've used y naught. And what's wonderful about this solution right here, what's wonderful about this solution is given an initial condition, x, given some y naught or some y naught of t equals to x naught y naught, I don't have to solve for any of the constants. I can just plug them in. This is where x naught goes, this is where y naught goes, this is where y naught goes, and this is a 0. So let's kind of do this in general real quick. So let me grab a drink. So right, finish copying that down. Degenerate system. Yeah, thank you. Was that weird to say? All right. So in general, oops, I already did that. So in general, how to find repeated eigenview general solutions. In fact, these are not only the general solution, but also the particular solutions at the same time, right? Because if the second you know the initial conditions, you can literally just plug it in. So we're going to find the values, and then we're going to find a V1. We're going to find the V1. We're going to find this V1 by doing the following. We're going to take A minus lambda times V naught, where V naught is whatever initial condition is. And then our solution is e to the lambda t, whatever my repeated is, V naught, where V naught is our initial conditions, plus t e to the lambda V1. This is not how your book does it. This is not how the book does it. Not the book's method. At least as I've lost my mind, I'm pretty sure I defer from the book real quick. Let me double check. iBook. I think your book uses a different method. I use this method, and it's the method I teach because it is so, it's cleaner, it's faster, it's more convenient. It is a little bit less generalized since it only kind of works for the 2x2 method. In that sense, it does have its drawback. Gee, I'm not positive I teach much of this section like the book does. Just putting it out there. Let's see what they do here. Yeah, they do something close to it. It's really close. You get it's just, they're equivalent solutions. And they get the repeated eigenvalue. They say this and this, and they put a t in it where x equals this. No, your book teaches more or less this, right? It's written differently, but it's not that far. So it's not the book method. Well, it kind of is. So we'll just get rid of that. All right, so let's find the solution. So we're just going to do the method from before. So we know what this is. We've already done this one. So here we're going to have find. I'm just going to do it by using this method. So here we know what the lambda values were. Lambda 1 equals lambda 2 from before, right? Equals minus 2. This is from before. Okay. All right, and so we find the eigenvalue, so that's step 1. Step 2 is we're going to find this v1. So we're going to find, we're not finding the eigenvalue. We're finding something that we're just calling v1, okay? v1. It kind of like an eigenvalue, but not, or an eigenvector, but it's not. Well, it isn't it? Just, it's something different. Let's just leave it that way. And so how do I find this? Well, I find this just by hand this. I want my cheat sheet in front of me. All right, so here I'm just going to take, minus 2 minus, so plus 2. So this is found by taking a, and in this case we minus, so minus becomes plus 2. Oops, I should have a tiny I in here, shouldn't I? It should be 2i. So along the identity, this is 1, 0, minus 2 plus 2. And I'm going to multiply that by x naught, y naught, because that's what v naught is. V naught is just x naught, y naught. So that's equal to 0, 1, 0, 0 times x naught, y naught. And if I just do multiplication, 0, 1, so this just is equal to y naught. 0, 0, so this is equal to 0. And then you just write out the solution. E to the minus 2 t x naught, y naught. I do not need a c in front of this because I've included my initial conditions already into it. So it's, do not need the c. Lambda, in this case is minus 2t, and then it's y naught. That's all you have to do for the repeated. So let's do this one for repeated eigenvalue. All right, so let's calculate this one. All right, we'll go through all the steps. So we're going to find, so we find lambda, that's step 1. Step 1, find the lambdas. And so this is minus 5 minus lambda, 1, minus 1, minus 3, minus lambda. Add in 5s. Minus 5 minus lambda times minus 3 minus lambda plus 1 is equal to 0. Multiply that all out, you're going to get lambda plus 8, lambda plus 16 equal to 0. So we have a lambda plus 4 squared equal to 0. So lambda here, lambda 1 equals lambda 2, which equals minus 4. So we have a repeated eigenvalue. Once we have a repeated eigenvalue, we're going to be using these steps right here. So the next thing we do is just find v1. So v1, so I'm going to find my v1. v1 is found by taking 5 minus 4, so it'll be plus 4. 1, negative 1, minus 3 plus 4 times x naught, y naught. Go ahead and make this easier for us. Let's just do the math. So this will be minus 1, 1, negative 1, 1, x naught, y naught. And so this is equal to y naught minus x naught, y naught minus x naught. And so our solution here is, and so here we can write out our solution. Y of t is equal to e to the minus 4t x naught, y naught plus t e to the minus 4t y naught minus x naught y naught minus x naught. How did I get that? I just said I get negative x naught plus y naught. So I just wrote it as y naught minus x naught. And then I'll get negative x naught plus y naught. Once again, I wrote it as plus y naught minus x naught, just so I had one less symbol to write. Now we're going to plug in the initial conditions, and I want to show you how amazingly easy this is. So we're going to do the initial conditions. In this case, it's minus 4t, x naught is 1, y naught is 2, plus t e to the minus 4t, y naught is 2, minus x naught is 1, y naught is 2, minus x naught is 1. There. I have solved for my initial conditions. So it literally could not be easier. I say that. You guys ever seen like Garfield and Friends where they have like the USA cruise and it's like, that's the laziest request I ever had. I'll give you $1 if you can think of one thing lazier to ask for. Yeah, and Roy Brewster just rolls over. Yeah, just slip it in my pocket. I don't know if you guys ever watched that. It was on when I was a kid. The old Garfield and Friends. Anyways, either a sip of water or bad stories when I was used to it. All right, so let's go over this. I think I do. What do I have here? Okay, it's a kingfisher bird. Thank you, eyedropper. I don't need to see a kingfisher bird. All right, so let's do. Yeah, right page. So let's talk about how to draw these real quick. All right, so here we're going to have a repeated source, repeated sink on this. And so, and you can determine this. So here, if I have, I think this is the one where I have a 0. Yes, this is where I have a 0. Where we'll find the general solution, sketch the phase plane. Here, I'll show you how to sketch the phase plane for the one we just, I think that's, yeah, it's the one we just did. So I'll show you how to sketch this. So let's do this kind of slowly. So there's going to be a couple things. So here, if I have lambda 1 equal to 0, it's going to look a lot like, it's going to look a lot like, it's going to look kind of interesting. So you're going to have whatever your, so this is going to be your 0 eigenvector.
Sorry to interrupt. I just want to make sure that's not like a lambda 1. That's just a lambda, but a lambda equals 0 because it's both lambda 1 and lambda 2.
So this is lambda. So one of the lambdas is 0.
Oh, just one of them.
Yeah, just one is 0. That should give you a hint of what to look for the extra one. Because I'm not going to discuss one of the systems, but it should be obvious now. Anyways, so if you have 1, you're going to have whatever your, so this, your B lambda 1, you're going to have a line of equilibrium solutions. We'll actually show this in that. And then the other ones are just going to kind of either go out or in, depending on that. Okay. And so technically here, I've shown you a lot more than that. So this can go out, this can go in, and yeah, you can declare those to be 2 different ones, right? Here, if I have a repeated source, you're going to have a single lambda value, right? And then it's going to go, and so this one will shoot out, and then these will kind of curve within that space. And so you'll have something with like curvature to it, and then we can have the same thing again, and then this time it'll kind of sink inwards. And so these are the types you can have. And so I'll have some sort of curvature to it. You'll have one line, you'll split the plane in 2, and you'll have some curvature. So you determine, and then to determine the direction of curvature, you just look at the same thing we taught you last time. we just look at the first one, the second one. Let's go back to this one. So here, let's go back. We already did this, so let's just steal our answer right here, right? So this is my repeated. That's right here. So let's grab this. So our general solution here is y of t equals to e to the minus 4t x naught y naught and plus e to the minus 4t. This was y naught minus x naught. This is y naught minus x naught. All right, I'm going to find the eigenvalue real quick just to kind of show you something. So I'm going to find lambda. So we never found that, right? It's not here. We found a v1, but what is v1? Let me find lambda real quick. So this would be minus 5x1 plus y1 equals minus 4x1. And this would be minus x1 plus minus 3y1 minus 4y1. I translate this all over, I get minus x1 plus y1 equals to 0. Minus x1 plus y1 equals to 0. This is the same, cross that off, move this over, I get y1 equals to x1. And so I get the v lambda, so I just plug in 1 and 1. Okay. Notice here that this, if you have this, every solution to this will be in this vector, right? Along the line of this vector, right? So no matter what x1 and y1 is, it's going to be the top and the bottom will be the same, so it'll be in the line of this vector. Okay, so you don't necessarily have to find this. You just plug in some random values here, like 1 and 1. Well, in that case, you get 0 and 0, so that didn't work. So plug in like 2 and 1, right? Something that's non-zero you can plug into there. You'll be fine. Or you can just find it the old school way. Either way works. So let's draw this by hand, and then we'll do it in the computer. So where's my vector? My vector is this way, right? So here's my vector. All right, and I know it, oops, I drew it the wrong way. Is this a source or a sink? It's a sink, right? It has negative lambda, right? So it's going to be pointing inwards. So this goes inwards. And so here, let's go ahead and clear this and draw our eigenline. So we've already established the eigenline we point in. So these are all going to curve in a very particular way. So how do we figure out what that curve is? By hand? Which none of you will do because none of you really have to do it. Just look at this, right? So here at 1, 1, I know it's going to come in. It's going to be mighty negative in the x direction, a little bit negative in the y direction, so something like this. And then here at 1, 1, it's going to be positive in the x direction 1 and mighty negative in the y direction like this. And so you can see that the curvature would have to be something kind of like this inwards, and also something kind of like this inwards. Okay, and so here I have it a little bit exaggerated from what it actually is so I have it exaggerated here. But you can see there is some curvature to the lines, all right? It's most exaggerated, of course, opposite from it. So that's how you draw those in. The only thing I haven't done for you yet is 0 eigenvalue. So let's do that. And once I've done that, we're done with chapter 4. I'm kind of curious that all of a sudden I just like disappear and say no one's the host. So Isaiah took over. Oh, good. He did well. All right, guys. So let's do this one. So here we're going to just find the eigenvalues. I don't know what system this is. I just say find. This is how the exam will look. Find general solution in phase find. It will not tell you what to do. Okay. All right. So in this case, we're going to find the eigenvalues. And so here, we're going to find lambda. So this is 4 minus lambda 2 to 1 minus lambda. This is going to go ahead and crunch through it. And you're going to get lambda 1 is equal to, oh, I'll go ahead and show all the steps. So this is equal to lambda squared minus 5 lambda, which implies that lambda either is 0 or lambda is equal to 5. So if you have lambda equal to 0, the next step is just to find the eigenvectors, because technically this is repeated and different, right? So you're just going to use that method. So v lambda 1, or v lambda 1, where lambda 1 is equal to 0. Here I'm going to have 4x1 plus 2y. And once again, you can use the other method I taught you. This will be 2x1 plus y1. Define your vectors. I'm just doing this way because this way it's very clear on what's going on with the equations. This is the same as this. This multiplied by 2, so you get rid of it. And so here I'll have 4x1 equals minus 2y1. And so v lambda 1 is equal to minus 2, 4. Do v lambda 2. Where lambda 2 is equal to 5. So we'll have 4x2 plus 2y2 equals 5x1, or 2, sorry. And then 2x2 plus y2 equals 5y2. We translate that over, we'll get minus x2 plus 2y2, and then we'll get minus we'll have 2x2 minus 4y2 equal to 0. Notice these are the same, multiplied by negative 2. Go to that. And so I have 2y2 equals x2. So here we have v lambda 2 is equal to 2 and 1. All right, so we have our, so we can do our general solution now. So y of t is equal to our c1 e to the 0t. So e to the 0t times negative 2, 4. I'll be pedantic about it, and then I'll show you how to just simplify it to e to the 5t. E to the 0t is just what? 1. So it's just negative 2, 4 plus 2 e to the 5t, 2 and 1. So how do we draw this? So the main point is, how do we draw this? All right, so anything along the line of anything along the line of negative 2, 4. So I'll do this. So we'll go over negative 2 in the x, and then up 4. And then here we're going to have, these are going to be a line of equilibrium points. And I'm going to represent that with dots. That's just how I'm going to represent it. Okay. So this right here is a line of EQ. Because notice, if we go back to, if I look at, notice here, that if x was negative 2 and y was 4, my change in my x would be 0, and my change in my y would be 0. So it'll just sit there, right? There is no movement. If my x was minus 1 and my y was 2, this would also be 0 and 0. And if my x was positive 1 and my y was negative 2, this would also be 0 and 0. So this line, everything along this vector, is going to be equilibrium points. Okay. Then, and notice here that this doesn't change in time. So if it's along C1, all my initial condition will be in C1, there'll be nothing in C2. But notice that after I choose C1 and C2, I'm only going to progress in which direction? This direction. So 2, 1, right? So here's my vector right here. And so it's only going to go out this way or out this way, and that's positive. And the same thing here, out this way or out this way. Out this way or out this way. And so you're going to draw this line of equilibrium points, right? And then from there, you're going to use this to draw the rest of it. And it's just going to be, and every line here is going to be parallel to it. Every line on one side is going to be parallel, and every line on the other side is going to be parallel to it. So let me show you this in practice. Let me show you this in practice in the program. Let's program. Thank you. All right, so what do we have here? What was my original one? It was 4, 2, 2, 1. Okay, so these are my eigenlines, right? And notice here that any point I draw here will be straight out from it, okay? And let's go ahead and do, let me mess with it a little bit. So that's how this one looks in there. So let me make another one. Let me make this a 3. Let's make this a -6. And then this, I guess I have to keep it a 5. Fine. Let me make this a 2 then. -2 and -2. Wow. Okay, that's not quite what I wanted to do. Here we go. So here we have another one, right? And so here are our eigenlines, but notice, so here, this is not, the other one was at 90 degrees. This one's not. This is my line of equilibrium points right here. All this are equilibrium points because that's the vector for 0. Then all the other vectors are going to be parallel to this vector, right? And this one's a lot more potent about it, right? And so you can see that they'll still, so whatever the 0 vector is, you're going to draw a little line right here. Let me clear it real quick. You're going to draw a little line of equilibrium points, dots. And then whatever your other vector is, you're going to just draw that in right here. And notice how this is negative, so it's pointing in. And then every line is going to be parallel to it until it crashes into the equilibrium line. And what does this mean? What does this mean? So it means if I started here, if I started at the point 0, x equal to 0 and minus, I don't know, roughly -2, right? Roughly. It means it's going to, this line is, the solution is going to go all the way up here until it crashes into this equilibrium line. Same thing if I started over here at 1.5 and 2. It's going to go until it crashes into here. And then it's going to stay at equilibrium. And so if you have a 0 vector and it's a sink, you know it's going to run into wherever the equilibrium line is and just stay there, okay? So it's going to slowly hit that in kind of an asymptotic behavior. Okay, so that's how you do with equilibrium points. I guess technically I have shown you all 10 at this point, and that's the end of the notes. Okay.